Good morning, everyone. Welcome to the short course on MTGI Flexible Combined Imager. My name is Natasha Strelec-Mahovic, and together with my colleague Carla Barroso, I will be moderating today's event. This short course on FCI on board the MeteoSat third generation imager satellite is the continuation of the series of short courses on MTG data and applications. Well, our Flexible Combined Imager on MTG satellite continues the very successful operation of the SEVIRI instrument on MeteoSat second generation satellites. It provides state-of-the-art observations of Europe and Africa for forecasting severe weather and for near real-time monitoring of the atmosphere, land surfaces, oceans. The FCI is essential for monitoring and forecasting severe weather events such as, for example, storms. It will also provide more precise information about fog, volcanic ash, air mass characteristics, clouds, and aerosols. And it will also assist us in the detection and monitoring of fires in particular. All this you will see and hear in this webinar. Now, before we dig into the wonders of our new FCI instrument, allow me a couple of minutes to introduce our organization to those that don't know us. EUMETSAT is an intergovernmental organization with 30 member states around Europe. The objective of the organization is to establish, maintain, and exploit the European system of meteorological satellites, and by this to contribute to operational monitoring of weather and climate. Headquarters of EUMETSAT are in Darmstadt in Germany. The organization provides observations and data services to operational weather services and other users in Europe and worldwide, supporting weather and climate monitoring and forecasting in partnership with other satellite operators and collaborations within Europe, the US, Africa, and others. EUMETSAT currently operates a constellation of 10 operational satellites, 4 in geostationary orbit and 6 in polar orbits. And the next generation of satellites is, as you can see, already on their way. One of them, the first MeteoSat third generation imager satellite, has been launched on 13 December 2022. The satellite is currently undergoing commissioning phase and is about to become operational really soon. One of the instruments is on MTG I1 is the Flexible Combined Imager that we are talking about today. In this 2-hour course today, you will get an insight into the details of the FCI instrument, acquisition of data and applications. The second part of the course will focus on data applications. You will see what images show in different real weather situations and how they are used for different applications. And finally, we will take a look at high latitudes, where FCI brings much additional information compared to our current imager SEVIRI. Our presenters today are Alessandro Burini and Ivan Smiljanic from EUMETSAT, and our guest Petteri Pikko from Finnish Meteorological Institute. We will take questions at slido.com, so please join Slido. I will just quickly put this here with the code EUMSC47, where you can put your questions during the talk. So, I will not take any more time from this interesting presentation, so I give word to Alessandro to start with the introduction of FCI. Alessandro.
Okay. Let me share the presentation. 1 second. Yes. I think you can share. You can see my screen now. Natasha, do you confirm?
Yes.
Okay.
Yes, we can see.
Okay. So this is actually the image that we received like half an hour ago from MTG FCI. It's so just to tell you that the data have been, let's say, they are streaming in our EUMETView system, you can actually see the images as they are acquired. Now you will receive like a stop of the data stream because we are uploading new settings on board. So we, as Natasha said, we are still in commissioning phase. So you might see some data interruptions. But basically, since June, we have a quite stable data stream now. I will give you now a brief overview of the mission, how it's been planned. So MTG is actually a constellation of satellites. We have two MTGI, which is actually our satellite. So it's the imager. On board, you have FCI that is scanning the Earth with from south to north with this, let's say, peculiar pattern. And then we have the lightning imager on board, which is a completely new instrument. It's made of 4 high-speed cameras. They are controlling the light, basically the lightning activity on the surface, in the clouds. Then we have the other satellites that will be completing the constellation, which is the sounder MTGS, and on board you will have the infrared sounders, the so-called IRS, and then you will have the ultraviolet and visible near infrared sounders, which is called UVN. Then we have the second satellite, which is a copy of the MTGI-1, which is called MTGI-2, and we provide the rapid scanning service over Europe. Just a quick overview on the timeline of MTG. It was launched on 13th of December 2022. Then we had the first image release on after almost 5-6 months, May 2023, and then the first image release for LI in July 2023. Then we started to try trial dissemination in November 2023. And then we formally concluded the instrument commissioning. So you have to consider that a system is made of two sectors: the instrument, which is something that you can easily make. It's a measuring instrument that is on board and has to be commissioned. Commissioning means that you have to learn how to operate. You have to test the instrument that is performing as expected, and then you have the so-called system commissioning. So it's the entire processing facility that has to be commissioned, so it has to be verified, and the system as instrument and processing facility integrated. So this is why it's a quite complex, let's say, operation. Then what has happened in January 2024, the instrument underwent a major anomaly. And I will show you some details and how we managed to recover from this anomaly. But there was a huge data gap from January to May. In May 2024, we switch again the FCI without the onboard calibration, and we will see actually what does it mean for the data quality and for the users. In July, we restarted the pre-operation dissemination of FCI, and now we are concluding let's say the last test on the system, and we will release the data in operational mode for the end of November.
Alessandro, can
Yes.
you just hide this little stripe that is hiding the bottom of the screen? Can you press on hide? Yes.
Yes.
Thank you.
So it's just to give you I will try to explain how the instrument is working, and I will give you this example. So our instrument in space is basically is working like our eye, and so this is something that everybody has, and we know how this is working. So basically, our eye is like an instrument, and we have a perception, or we can see colors, because in the back of our eye we have some detectors, we have some cells that are sensitive to colors or to light, and our eye basically is sensitive to this type of colors, to especially to blue light and to green and red light with this type of nice curve, which we call usually in our work we call the spectral response functions. So this is to give you an example on how we perceive the outside world is actually depending on the cells that we have in our eye. And since everybody is different from the others, probably we see the colors in a different way. Okay, so it's really subjective how we perceive the light. Said that, we have to consider that what we will see in space is actually a mixture of how the instrument is acquiring the Earth, and how we actually translate this light in our subjective perspective. So let's go a bit more in detail on how FCI is working. So FCI is actually this big telescope on MTG. So I hope you see my cursor. Is basically this hole here, which is the baffle, and then inside you will have you have the electronic and the instruments. It's basically made of a visible part, so a visible instrument that is acquiring the visible and near infrared radiation of the Earth, and then an infrared part. So it's actually, you can see FCI like two instruments in one that is focused on the visible part, and the other one that is focused on the infrared part. Why I say two instruments? Because basically the electronic that is involved in the detection of the light in the visible and then in the infrared are, let's say, different, and are completely different. They work in a different way. Just an example. To detect the thermal radiation, you have to cool down your detector plate, and you have to have a very stable thermal environment of your detecting chain. While for the visible channel, we have different problems. For instance, we have to have very clean surfaces, and the alignment of detector has to be really accurate, and we might have like stray light problems. So it's actually two different way of building the instruments. Everything then is integrated, and you have a scanning mirror that is actually performing the scanning of the Earth every 10 minutes. And why FCI is called Flexible Combined Imager? Because this way, this scanning pattern can actually be commanded, and we can perform several types of scanning of the Earth. So the nominal scan is the full disk, which is every 10 minutes. Then we have the rapid scan that is every 2.5 minutes over a subset of the disk, and then I will show you how it's possible also to do some special acquisition over a particular area. Say that we have the light that is coming from different, let's say, channels, basically different wavelengths. So what our instrument is actually doing is collecting the radiation that is reflected by the Earth and emitted by the Earth in the infrared domain, and storing to digital numbers. So what we actually see is it's a collection of colors that then will be translated into digital numbers. Let's go a bit more in detail on how the instrument is acquiring. So this scanning pattern that you have here on the bottom left is actually the scanning mechanism of FCI, and we receive basically 70 chunks, 70 swath every 10 minutes, plus one retrace that you will not see. It's the 70, let's say it's SWOT number 71 that is not disseminated. It's where all the calibration measurements are done. So these 71 chunks are then used to create the so-called level 1C image. It's actually a projection over it's an orthographic projection of this type of acquisition. And this is what on the bottom right, this is what you will receive, and what you get. It's actually an orthorectified and projected a rectified image on orthographic grid. And for doing that, basically, we are actually chunking. So it means that we are, again, cutting the level 1C data in chunk, and it's disseminated for over 40 chunks. So we are basically projecting from 70 chunks into a level 1C data disseminated with 40 chunks. Why we are chunking the data? It's just for dissemination purposes. In this way, it's possible to parallelize the process and to exploit the bandwidth in a better way. And also, we can disseminate a chunk as soon as it's produced. So basically, when you will receive data that is completing as it's acquired. This is what let's have a view on let's say on how what does it mean a fixed grid. The level 1C product is actually a cartographic space that you see here. It's a cartographic grid which is defined, and you have this type of definition. In the product, you will have three different grids: the 2 kilometer grid, the 1 kilometer grid, and the 500 meter grid for the let's say high resolution channels. You will see that the pixels are quite the image size is quite demanding. So you will go from almost 5,000 per 5,000 up to 22,000 per 22,000. And I can tell you that the 500 meter images are extremely big. So it's in terms of computing resource, or also the if you want just to display the image, you will see that you will need a lot of computing resources. So usually, as I told you, you have two types of acquisition, which is the full disk and then the local area coverage, what we usually call LAC. In the level 1C, you will receive only the Earth disk, so you will not see any deep space, so you will not see any star, and the data basically are masked. What we receive here in EUMETSAT is also the deep space in the level 1B, so we can actually do some measurements on the deep space, and I will show what I mean. On the bottom right, you have actually the schema on how the acquisition is performed. So you have the satellite and the Earth, and here basically the grid is so the surface is projected in a Cartesian space. This is what is being done, and in the end, what you get is actually a data cube. Let's go into some features of the satellite, so that you can of the sensor, sorry, that you can actually see which are the improvement of our new sensor. So here you see some. This is actually the first acquisition of FCI. Here you see the Severi natural color at 3 kilometers. So we have Severi that is acquiring the Earth disk with 3 kilometer resolution, and now you can see what the new resolution of FCI is looking like. It's a 1 kilometer resolution. And this is the 500 meters. So you can actually see the big step forward in terms of resolution and then details that can be captured from Seviri on the right. That is 3 kilometers to the highest resolution possible with FCI for the same channel, 0.6 micrometers with 500 meters of resolution. Again, it's just to give you again an example on how the instrument is bringing new information for the weather forecast. Is actually with FCI we see a lot more clouds, and this is what I can show you here. Again, we have Seviri, and here with again it's FCI. So you can actually see all the, let's say, small clouds that cannot be detected with Seviri. What does it mean in terms of capabilities? Yes, more clouds, it means you have more information. I can already tell you that more cloud means that we have also to update our algorithm, because we already discovered that more cloud, it means that we have to update the way we detect the clouds, and also we validate the cloud. So we pushing the resolution. It means also that we have to upgrade all the validation chain, all the retrieval chain for our algorithm. This will be, how you say, it's not trivial to translate the increase of resolution and also the increase of the spectral quality of the data into a better retrieval. I would like to give you now some examples on how this instrument is also improving the retrieval of fires, which is one of the application of, it's not the only one, but it's one of the application that you have with Seviri. So let's go with the basics. So each object that exists in our, let's say, in our world is depending on the temperature, is emitting a radiation. This is basically, it's related to the Planck law. So you will see that, let's say, hotter object will emit light in a higher wavelength. So, for instance, our sun, that is emitting at a peak of 5,000, almost 6,000 Kelvin, is actually emitting in the visible domain, and this is why we see. I mean, it's our eye is also sensitive to this wavelength, because he has to capture the light that is emitted by the sun. Depending on the temperature, we can have, let's say, peaking of the emission in a different wavelength. So, for instance, our Earth, that is more or less emitting at 300 Kelvin, has a peak at 10 micrometers, and this is why we have a window channel at 10 micrometer to measure the emission of. It's called window channel. It's something that is measuring directly the radiation emitted by the Earth. If we start to look into the application of fires, so we actually see that the fire, when start to burn, is actually emitting a light in different channels, and with the let's say hotter channels will start to emit also in the near infrared. So you will start to see actually the fire with the near infrared. So with FCI, we actually have these channels that are dedicated to fire monitoring, so 1.6, 2.2, 3.8, and then also the window channel 10.5. Particularly, we have a channel that is dedicated to fire monitoring, which is basically, it's done in a way that it's not saturating, so we can actually retrieve also the 5 radiating power. The way the fires are actually retrieved, it's quite simple, because you can imagine that there is a fire that is starting in the 3.8 microchannel. When the temperature goes up, basically this channel is going to saturate, and you will start to observe the fire, and also with 2.2 and 1.6 channel. When you start to see the channel, the fire in 1.6 in the 1.6 microchannel, it means that the fire is very extremely warm. So in this way, we have using the spectral information coming from different channels, we can actually come with an estimation of the fire temperature, and thanks to the let's say on the non-saturation or the extreme broad dynamic range of the 3.8 channel, we can actually perform a retrieval of the fire radiating power. The observation of fires is actually done at 2 different, let's say, different resolution. We have the usual 2 kilometer resolution for the basic resolution of the infrared channels is 2 kilometer. For this particular channel, so for the 10.5 and 3.8, is actually, we have also the high resolution transmission of the channels at 1 kilometer. And then we have the 500 meters for this particular channel. So for the 0.6 and 2.2, we can have also the 500 meters. So for instance, for the observation of fires, we can actually go to 500 meters to observe some particular fire events. It's important to see how the grid are actually co-registered and stacked in a way that you can go from the 500 meter grids, you can actually locate the subpixel in the 2 kilometer grid. So the data are stacked in a way that for the user is actually convenient to go from one grid to another. It's basically what you are receiving. You will be receiving is actually a data cube. So it's really convenient to go from one grid to another. Let's go with some example on how the fires can be observed. So this is actually a visual rendering on a fire event that occurred basically 1 year ago in Sicily. You can actually see this is a true color image. So it's a combination of the visible channels plus the infrared information. So here it's basically the blending of the visible channels plus the 3.8 and 2.2 micron channel. It's a short animation of data from 1 year ago. You can still actually see some wobbling of the image, and this was due to the commissioning results. But you can actually see how good the fire can be observed with FCI, and actually you can see how the smoke is transported by the winds up in the north. This particular fire event was related to quite a major evacuation in Sicily. So it was a fire near to a touristic area, and many people were to be evacuated. This is another example that we perform in commissioning. It's a fire event over the Rhodos Island. But this particular event was performed with a rapid scan. So the image that you see here is actually the evolution of the fire every 2.5 minutes. So you can actually see how the fire can be monitored and how the animation is smoother. I hope that is also smooth for you. Now let's go to the latest observation. So this is the last fire event of Athens. So this summer, 11 of August. Again, it's always the same true color image with the fire channels blended on the top. But you can actually see how the instrument is capable of capturing the evolution of the fire, so the starting up of the fires, and then the transportation of smoke and the detection of smoke way in the south, so from Athens way to the south of Greece. And this is something that is also that we wanted to observe, is the eruption of the Mount Etna, always this summer, 4th of August. So this is actually not a fire event, but is the emission of lava from a volcano. You can actually see some small fires on the way in the north here that are just starting up and are closing, very small fires. But it's interesting how you see how we can actually detect also the eruption and how the let's say the smoke is transported in the atmosphere, and actually we can see a different color of the eruption event. You start to see a more brownish color of the gas that have been emitted by the Mount Etna. Again, these are actually the latest data, and you might notice how the quality or also the stability of the image improved. So this is really close to the data that you will be receiving in a few months. Another example is this is quite recent image, like almost a month and a half ago. It's the transportation of the smoke event coming from Canada, 19th of August this year. And you can actually see how an event that occurred from basically in Canada has also an effect on our continent. So what you see here is actually the smoke that has been traced back to the Canada event. So you actually see how good is this instrument also in detecting this type of event. Let me give you, for the ones that are more familiar with coding and playing with Python, we also released a software suite which is called Pytrol. We are contributing to the Pytrol initiative, and actually you can pull the code that can give you the possibility of creating by yourself these images. So it's you have the tutorial, you have all the information to create RGBs and animation and images by yourself, and you can actually easily process the FCI data. What you see here is the so-called geocolor. Basically, it's a blending of the true color with a night layer with a special color system so that you can actually recognize the low clouds, high clouds, and some other layers. Another nice example this is actually just a type of curiosity. This was an event that occurred last year, the eclipse. You can actually see how the shadow of the moon then is projected back on our Earth surface. This was on the Brazilian area. Let's go into let's say a more experimental view of FCI. This is the so-called super rapid scan. So it is something that you will never see into operations. It is actually the observation of convection over Africa with a temporal resolution of 40 seconds and a spatial resolution of 500 meters. So it's the first time that we in Europe we can observe a convection with this temporal resolution and also with this spatial resolution. And this was an experiment that we ran last November, over Central Africa. So we commanded FCI to perform basically a kind of stare and look acquisition. We commanded the FCI to observe Central Africa with 4 consecutive swaths every 40 seconds. And this is actually the results of the observation. So we could observe how the convection is growing, burning, and with high resolution. And at some point, you will start to notice also the overshooting tops and the evolution of the convective cells. You will see a jump in the image, because basically we had to command the sensor into calibration mode every 10 minutes. So we actually acquired the images every 20 minutes and then a jump of so for a time window of 20 minutes, we acquired an image every 40 seconds, and then we had to jump of 10 minutes. We had a jump of 10 minutes to perform the calibration. Very recent images. Now we have the instrument that is actually working in a continuous way, because we managed to have a stable processing and a stable event, a stable processing chain, and also stable acquisition. So we start to receive images and also data in a more fluent and more stable way. So we can actually start to perform and to use the data in a more useful way. So this was a particular event that occurred over the Baltic area with it was actually a severe event where these countries, Lithuania and Latvia, suffered by a strong event. But it's actually important to see how the different bands of FCI can be blended together to observe the event with different spectral information. So here on the left you have a true color image at 1 kilometer. On the right side you have a cloud phase RGB at 1 kilometer that is giving you basically the phase of the clouds, of the content of the clouds, if it's a water cloud or a ice cloud. I'm sure you will have more information later by Ivan. Again, another view of Italy here, and what I wanted to show you is the capability of the instrument of detecting also the contrails. So here it's a nice view of contrails, how they are then transported way up to the north. It's an animation of 4 days, so you will see it going from daytime to nighttime. But actually, this type of observation is something that is really new for this type of instrument. So it's with Severe it was not possible to achieve this type of resolution and this type of detection for this type for the contrails. Another view is, it's the observation of convection over Italy, South Italy, always this summer. We can actually see how the convection is evolving and is being created during these days for South Italy. I'm an Italian myself, so I can tell you that these type of events are quite common in Italy, but they are really violent. So they could create a lot of problems. And this type of observation, so the new sensors with the new temporal resolution will give us hopefully some early warning for this type of events. I can tell you that this type of convective cells coming from the sea and from the mountains are usually, and especially in August, are usually full of water, and the wind is tremendous. So usually they create a lot of problems in our country. Just a quick overview of over the northern countries. You will see more example in a later presentation, but this is to show you how the increase of the resolution and also let's say a particular projection can give you a useful observation also over high latitude, which was not possible with Severi. So here you have an animation of 4 days, again over Norway and Sweden and Finland. You can actually see how it is possible to observe the weather events over this high latitude. Let's start now with some more, let's say, technical details on how the instrument is behaving and is performing. As I told you before, this is basically the timeline of the lifetime of the instruments. We started to observe in March. So from March to November, we performed the instrument commissioning. So we started to, let's say, to play with the instrument with different modes to test all the functionalities of the test, and also how to learn how to operate the system. And then in January, we had the so-called COM anomaly. And I will give you now some details of what does it mean for the user, and what does it mean also for the operation of the instruments. So the COM is basically, we started to have problems with the acquisition mechanism of the FCI, and we basically lost the onboard calibration source. We performed some offline tests to come with a solution, and then in May, we managed to switch back FCI on with a complete brand new calibration system, and I will show you what this means. So a few words on how the instrument is calibrating, or how the calibration is working. So the concept of calibration is really something that we all know. For instance, a thermometer. The way of calibrating a thermometer is pretty simple. You have a thermometer, and you put it in the boiling water. You know that it's 100 degrees. And then you take the same thermometer and you put it into the melting ice, and you know that it's at 0 degrees. And in between, you start to put basically 100 small lines, and then you basically calibrated your instrument. You have a calibrated thermometer now. The same concept can be translated into FCI. So you have, as I told you, you have two instruments in one. You have a visible instrument, an instrument that is acquiring the visible radiation, an instrument that is acquiring the thermal radiation. For this reason, you have two different calibration bodies. One is the black body, which is pictured here, and it's a calibration device for the thermal radiation. And then you have the so-called MND filters, which are basically two filters that are used to look at the sun and to have visible calibration, to have visible reference sources. Why we have two filters? Because as for the thermometers, you have to perform two measurements for having, let's say, two reference measurements to have a calibration curve. So here you have, let's say, a high filtering, a high filter, and then a low filter. So we have actually two different measurements of the sun, and this is done when the sun is actually showing up during the in March and September. We will have the sun intrusion in the field of view, and what we used to do was to command the shutter, so this device, to command the COM device into MND filter 1, MND filter 2, so that we could observe the sun through the different filters, and we could actually have calibration measurements for the visible channels. Why we have only one black body? The reason is quite simple, is that because the black body is actually a kind of radiator, black radiator that is thermally controlled, and we can actually command the black body to have low temperature and high temperature. So we can actually have two measurements for the calibration also of the thermal channel. This is a kind of revolving wheel that is exposed, and it's used to close the optical path of the instrument. And during the scanning of the Earth, so you see that in this way, in this picture here, where you have the disk and you have the scanning pattern of FCI, what was happening is that we had a deep space measurement at every scan, and when we arrived to the north, then we were performing the so-called retrace scan, where this wheel was commanded into the black body position, and we were actually performing the black body calibration. This was actually performed every 10 minutes, so every repeat cycle. It means that we had a black body calibration every 10 minutes. Why this is important is because in this way we could actually control the evolution of the thermal channel, and we could actually keep all the calibration and stability of the thermal channels as per user requirement. In January 2024, this device stopped working. The nominal side of this device was basically malfunctioning. And after a lot of iteration with the industry and ESA, and then we decided to leave the instrument in free beam, so to stop commanding the wheel into calibration mode. And this had immediately an effect on the data, because basically we lost our calibration bodies for the visible and the infrared. And now I will show you what this means in terms of operations. What we managed to do is actually to use a different instrument, which is YASI, to perform a calibration. So we use YASI as a reference instrument to come with with calibration coefficient for YASI. So it's actually a technique that is putting together FCI data and hyperspectral data from a LEO sensor, so from a low Earth orbiting sensor, and we managed to come with a calibration. You see here basically the spectral response function of FCI into the YASI spectra, and these are actually the if you remember the idea of the eye that I give you at the beginning of the presentation, these are actually the bands or where the instrument is sensitive to radiation. This is an example on how it's a functional test. That it's what we put in place with preprocessed data. Here is actually, you see how the calibration or all the black body measurements of FCI are acquired every 10 minutes. And here you see the first gain from the internal, from this method, so from YASI. You see how a randomic gain was put here, and after 24 hours were recovered thanks to the calibration with YASI. As you see, at the moment, it's a statistical method. We can actually retrieve one gain per day. We are working now to increase the frequency of the calibration, but it's at the moment the quality of data is the nominal quality of data has been completely recovered. Just to give you some, let's say, some plots of how this, let's say, vicarious calibration method is working. Here you have the intercomparison of the FCI channel versus YASI for all the thermal channels from 3.8 up to 13.3, and you can actually see how the calibration is kept into the user requirement, which is this red box. So with this method, we could, let's say, patch the loss of the calibration wheel. You see that basically what's happening is that why we have to perform calibration. We have to perform the calibration because the instrument is evolving in space. Because if you remember the example of the thermometer, you calibrate the thermometer once and then you don't touch it anymore, because basically the instrument is not evolving. Our instrument in space is actually evolving. And why it's evolving? Because it's in a particular environment, and it's so complex that some parts are changing in time. In particular, for the thermal channels, the evolution of the thermal channels is related to contaminants that are still in the instruments. So some molecules of water vapor that are in the instruments. And due to the low temperature of the detector plate, so if you remember, I told you that the instrument has to be kept to a very stable temperature, very low temperature. Basically, we have ice that is building up on the detector plate and is changing the transmission of the light from the camera to from the CMOS detector. And for this reason, we have to change the gain. So we have to increase the gain, so the sensitivity of the instruments, in order to compensate for the ice that is building up on the surface. You see that is actually pretty linear. I mean, the degradation of the gains is pretty linear. I can tell you that nothing is perfectly linear. And why we have to perform this calibration? Because after I don't know if you're familiar, for instance, with amplifier, but basically you cannot set a gain up to a certain level, because you will have saturation at some point. So for this reason, we have to keep everything at a level where the saturation is avoided. Visible channels, we lost also the calibration for the visible channels, and for this reason we put in place another vicarious calibration. So we are using the Sahara Desert as a reference, and we are monitoring and keeping the calibration also of the visible channels under control. Here what you see is the data gap that we had due to the anomaly, but actually when the data flow restarted, all the data are basically within specification. So everything that is around 1, it means that the agreement between the instrument and the simulation are pretty good. There is an exception for the near 2.2 channel, which is showing, let's say, a bias of around 8%. This is actually under investigation, and it's probably due to let's say, a bad characterization on ground of this channel, which is also common to other instruments. So this is actually this is what I wanted to show you in terms of instruments, how the instrument is calibrated, performed, and how is it performing. Just to mention that we are actually calibrating the instrument with a vicarious system, but the quality is kept under control. Probably we will face other challenges in the next future, but it's something that is, let's say, put into the budget. We will look into these other problems. Since the 25th of July 2024, we have data in pre-operational. And since September, 25th of September, data are going to all the users. We are scheduling to open the operational dissemination in end of November 2024. So that will, let's say, will be at the end of the commissioning of the FCI 1. I would like to leave you with this last animation, and this is the FCI blended, so it's the geocolor of FCI blended with also with the lightning images. So this is to give you a flavor on how the instrument will perform. I mean, is performing actually in combination with the lighting. Powerful is instruments observing the weather phenomena, so you can actually observe the cloud, but also the lightning emission. So the type of information that will go to our user, our forecaster, or to ECMWF is really a huge step forward compared to what we had with Seviri. And now it's I'm available for questions if any.
Yes, thank you very much, Alessandro, for so much information. I hope the listeners were happy with all the explanations. There are a couple of questions. I can even share my screen so we can go one by one
Yes.
rather quickly to answer it, to give chance to other presenters to do their job. So how is the water vapor channels, water vapor 6.2 and 7.3 measured? That's the first question.
I mean, what does it mean? How is it measured? It's measured as all the other channels. So we have 3 detector plates, IR1, IR2, and IR3. These 2 channels are on the IR2 detector plate, but it's basically the same way of measuring as all the other infrared channels. So maybe I didn't understand.
Okay, we can think of it and then answer in writing, maybe. Okay.
I mean, I don't see any particular problem with those 2 channels. We have some issues with the channels in terms of performances, but in terms of way of detecting these channels are.
It's the same as all other infrared
exactly
channels.
yes.
Yeah. The other question was in the Mount Etna loop. Is the dark brown color of eruption from the large concentration of?
Yes. Yes.
Okay, so do you have any idea which version of RT-tau from NWP SAF will have MTG FCI in it? No.
No,
okay.
But we can come back to.
Okay, we can answer this one later. Are there any case studies for ocean color?
Yes. So it's still not public, so you cannot look at the results, but there is a study to use the FCI also for ocean color, because we noticed that actually we could observe some ocean feature and ocean color with FCI. I didn't receive the final presentation and the final result for the study, but yes, there is absolutely an interest for, and there will be application also for ocean color.
Okay, so will the normal set of RGBs, ERMA's microphysical fog, be kept? Yeah.
Yes, absolutely. Yes, with some new RGBs, of course.
Of course. Is the data from FCI going to be in principal components and not data counts, which was the case with Severi? What does it mean for the users?
If I recall, the FCI data are not in principal components. I have to check if there will be also this type of dissemination. So principal components it's actually a way of compressing the data, representing the data in a different space. So what does it mean for the user? That if data are disseminated in this way, as in for Severi, you need a decoder to reconstruct from principal components and go back into the radiant space. At the moment, what I know, I have to cross-check because you never know, but FCI is disseminated with normal channels. So you will
in counts.
In counts. So when you open the data, they are stored in NetCDF. You will have all the counts and all the information to calibrate the data. What I recommend is actually to use Pytrol. If you want to work with data, it's very convenient to use the Pytrol suite because you have the readers and they will perform the calibration and the translation of from the counts to physical space for you. It's already tested. It has been developed in collaboration with the Python community by EUMETSAT. So the reader has been done from us. So it's actually really convenient for users. If you want to work with this type of data, don't start from scratch. Go and join the Python community and use the Python suite because it's there. The reader is there. You can expand your code from there, and it's actually really, really convenient.
Yeah. Okay. So I have an answer from Stefan here, who is so there is no FCI data in principal components. Yeah. It's in form of NetCDF compressed in near real time. And you already answered also the question. There is a reader and SAT file
yes,
for
yes,
MTG
yes,
FCI,
absolutely.
So
and we are maintaining it, and it's
yeah. So is there a timeline for the correction of the striping artifacts?
So what I didn't show in the presentation is so the difference between Severi is that yes, FCI is prone to stripes, and it's prone to stripes because we are using a large detector. So we will have two types of stripes actually. The interpixel dishomogeneity or non-homogeneity of the pixel, and this is actually more or less kept under control, but you might see some residual stripes. Or also let's say some noise can happen in the detector chain. So you might see some, let's say, interpixel stripes, especially on some homogeneous area or some particular clouds, or when you perform for instance, on the dust RGB, we notice that you can see actually some striping effects over the clouds, especially when you do the differences between some channels. You amplify this type of effects, and then you will see that you will see some banding effect due to the stray light correction. We are still working on it. So you might expect some banding effect on the 12 and 13 channel. The timeline for the mitigation is something that will arrive in, let's say, 6 months from now, something like this. And we will be, let's say, it's actually our priority. But so the interpixel channels, we stay there. Probably you might see some stripes showing up and going and disappearing. That is the nature of the instrument. Usually the stripes are kept under control. The bending effect is something that is more long-term correction, and we are still working on.
Okay. There are still a couple of questions. I suggest that we answer them in writing because, if you
Okay, radiosonde used, I can tell you, radiosonde cannot be used to calibrate the data. That's no.
Okay.
It's a no.
Yeah, it's a no. And then so is there a timeline for nowcasting soft package? We will answer then in writing. That's the question for nowcasting.
So the radiosonde, I can tell you that we use the radiosonde to validate the level 2 product, not to calibrate the level 1.
Exactly.
It's a different domain.
And okay.
Provide updated uncertainty characterization. This is also in the pipeline. We would like to have an uncertainty per pixel in the product. We had actually other priorities, but this is in the to-do list. Yes.
Okay. Okay. Thank you. So we will answer the rest of the questions in writing.
Okay.
And I suggest that we move on. Thank you again, Alessandro. This was really informative. And I give word now to Ivan, who will talk a little bit about the applications. Of course, you can still post the questions on Slido, and we will try to answer them at the end of this talk. Thank you.
Hope you can hear me, first of all, see me.
We cannot hear you really well. You're very, very silent.
Okay, yes, good.
Now it's better.
My microphone was up. Good, thank you, Natasha. So after Alessandro gave you the input to how the instrument is working and what are the technical aspects of the instruments, giving some examples, I will use another 25 minutes for quickly overwhelm you with the nice imagery of FCI. We do not have the data for a long time, but there are already so many interesting things to show, and unfortunately not enough time here to explain everything. But if you come out of this session with the incentive to go back to the imagery and look for yourself, it's a good invested time. And just a disclaimer at the beginning, I will focus on the products that you have available in the EUMETView viewer since I think a week ago. So you can go just after this session yourself and check the EUMETView, view.eumetsat.int, and you can explore the imagery yourself. All right, so what is FCI? It's basically a new version of a severe instrument that we had so far with the EUMETSAT satellites, and it's more of evolution than revolution. I have to say that our severe satellite is already a really good instrument, and we were far ahead of the rest of the world before they introduced the third generation of imager with Severi, with the 12 channels and the resolution of 3 kilometers. That was really a good instrument, and so we are stepping kind of moving a step forward, like the evolution of, say, African eagle you're seeing here, representing kind of the flight of Meteosat above Africa. The evolution of how the bird with years, hundreds of years or millenniums, getting better eyesight, more colors, maybe better focusing. This is how we moved from Severi to FCI. In terms of resolution, that means spatial, and not only spatial, there is temporal. We have a much better revisit cycle. We do have spectrally more channels, which give us more colors, so to say. You will see what are the applications of that. And in the radiometric sense, we measure the finest details of difference in cloud temperatures or reflection from the surfaces. Given better spectral resolution, we can provide more RGBs. Someone asked, do we keep the RGBs? Yes, we keep all the Severi RGBs, and you can see there are not given birth from the additional spectral channels here. Around about 4 or a couple of more maybe in the future, we will have from the new imager. And these are well established with ABI and AHI, Japanese and US imagers. And these are true color, cloud phase, cloud type, and fire temperature RGBs. I will mostly focus on the true color and cloud phase. I will give you some other examples, but as I said, it's too little of time to show everything and cover all the application areas, which are really various from, we've heard, ocean colors to convection. So let's see some imagery. Okay, I start with the cloud type RGB, and as Alessandro was pointing out, it can really nicely show the thinnest clouds up there, especially at the higher levels. So thin cirrus clouds, in this case, associated to tropical cyclone Isa, in this case, over Australia. And you see some stripes here and missing data. So why am I showing this? This is because to point out, before we had the FCI instrument, we were preparing ourselves for it with proxy instrument. And in this case, this was SLSTR on board Sentinel-3, where we were trying to test how this cloud type will look at the tropical cyclones. And on the right-hand side, how this new FCI imager with its 0.9 channel will look at the low-level moisture. So you see with the introduction of this tropical cyclone, there was a pool of moisture over the continent. And in the dark shades, you see the call it dry line, and the deeper gray means more moisture in this case. You will see example at the end over Europe. Okay, this morning we are showing the EUMETSAT RGB. This is standard RGB that was also introduced with Severi. And actually, what you're seeing here is Severi image. But why am I showing Severi image? Just to point out that some RGBs and some values of Severi are still there. Looking at the synoptic scale here, with some convection over central Mediterranean, we're looking at the remains of Hurricane Kirk over the Atlantic Ocean, cold air mass in the north in the deep blue shades. This all will be still useful with Severi, equally useful with FCI, if not a little bit more. But if we want to utilize FCI, we need to look at a little bit more details. Okay, just accompanying image from FCI. So what you're seeing is geocolor, and it means in the nighttime, so left of terminator line, more or less you have infrared information. Blue is low clouds, white is high clouds, and on the right-hand side, you have a visible true color imagery attached to the daytime scene. So you see there's a lot of information, a lot more than a EUMETSAT RGB, especially when you look at the clouds and the smaller cloud features like fog. We'll come to that. But you can also see the discrimination between the high and low clouds and some foggy areas probably around the Iberian Peninsula here, and many other things that are utilized from 2 kilometer infrared information during nighttime. Just zooming in a little bit, on the left-hand side, you're seeing a nighttime view of this geocolor RGB, and you see the fog very well, actually. So we're using 2 kilometer information here in blue shades. These are low clouds. Is it fog or a stratus? We don't know, but in terms of fog, we can, especially in these valleys, we can associate stratus clouds with fog. And corresponding image on the right-hand side is a visible one, actually true color RGB, which does not discriminate the high clouds like on top right corner, and the low clouds, but we do have advanced resolution here, and we can really see the fine lines of the valley fog, especially here behind Carpathian Mountains. You see really the smallest filaments of this stratus cloud. What else this morning? Looks like a not very interesting view over the Eastern Mediterranean. However, it reveals two important bits of this true color RGB or geocolor during daytime. And that is here in this valley behind the mountains around Tarsus. There is a kind of a blurry scene, some kind of a hazy aerosol aloft. And this is one of the advantages of true color RGB. It can very well see the smallest particles in the air, like smoke, dust, ash. You will see more examples of that. This is just to show that if you compare this to, for instance, Seviri product, natural color RGB, which is the closest one, you will see how less of these particles you can see at the same time. What else you can see, of course, if you pay attention to Egypt down there, you see there's a difference definitely between the vegetated and bare grounds. And there was a question about the ocean color. At the mouth of the Nile River, there is a lot of deposit, and it produces, gives nutrients, but also produces the turbid waters, all of which can be seen also through this product. So ocean color, not as good as, for instance, Olch instrument, but still very useful, global scale every 10 minutes. Yeah, moving away from Europe for a moment, we moved over the Atlantic a couple of days ago. Hurricane Kirk, tropical cyclone Kirk, spinning nighttime, again, infrared imagery, 2 kilometer, already very good at this synoptic scale, looking at the synoptic scale. Also for a contextual awareness about where the cyclone is and where these rain bands and how far does it expand, where is the eye of the hurricane. This is already a very useful information looking from far out with infrared, 2 kilometer or daytime, 1 kilometer, where you already start to see some cloud top features, some filaments of extended cirrus bands all around the hurricane, eye wall, etc. Of course, we can zoom in, and if we zoom in, we really see how good this instrument is. This is the same hurricane looking from very close. You can see the fine structures on top of the eye walls and also on top of the rain bands around the hurricane, all of which is very essential for instance, Dvorak analysis of hurricanes and assessment of the status and future development of such tropical disturbances. Let's move over Africa, and we're again looking at the same geocolor RGB, very faint in the morning. So that's a couple of days ago, 3 UTC morning over Eastern Africa. Why is it so pale? Because when you move to short wavelengths used in this RGB, then you have a lot of sun glints. So you will see the sun glint. If I move the animation forward, you will see how this glint is moving towards the west. And eventually we get very nice view over the scene. I'm having a little bit of trouble navigating through this animation. Anyhow, at this point, there's no sun glint, and you can see all across the Eastern Africa small cumulus developments. So the diurnal heating is kicking in. There is a lot of moisture, so the small cumulus clouds are building up, and eventually in the afternoon will turn into serious thunderstorms. Similar over the northern coast of Somalia, here over the Yemen coastal regions. Also, you see this small patch of clouds associated to the summer monsoon, which already passed, but still a little bit ongoing. This low-level jet from Somali low-level jet going northeast, still active, and all that you can see in one static image. But if you move, it will become apparent what is the dynamic of the atmosphere, how high the clouds are. For instance, these thin cirrus clouds moving from the east into the scene. You see they have a different direction than the low-level Somali jet or the clouds associated to this jet, or development of the sea breeze affecting this low-level formation of cumulus clouds, but also giving additional forcing for clouds to develop even more vertically. For instance, in the north of Somalia, you see stronger vertical development later in the afternoon. Also, a little bit later over Yemeni's southern border. But how do we know these are high clouds? Of course, from the contextual story, looking at the temporal development of the clouds. If you're a meteorologist, you would definitely know how to interpret the dynamics of the clouds, not knowing really the microphysics. But really, if we want to know more about what the clouds are made of and in which state of their developments they are, we need to know something more about the microphysics. Hence, we're moving to cloud phase RGB. And this cloud phase RGB is not only telling you about the cloud phase, in this case, yellow to purple. This is water clouds, and everything that is blue, deeper blue to light blue, this is ice particles. On top of that, there is a gradient in colors which also can tell you more about the particle size. For instance, for the ice clouds, the lighter the blue, the smaller the ice particles, and the more active the cloud vertically is. So if we move the same animation through time, you can see that, okay, it's jumping a little bit. I cannot stop it, I guess. You can see initially that all the clouds are yellow to purple. Gradually, throughout they change in color to blue, which means they move to ice phase, and then they become more dangerous, showing really pale blue signatures of top of the cloud, meaning that they reach the troposphere, tropopause, and they have a small ice particles and strong vertical updraft developments. So there is much more to say about this cloud phase, but let's move to more zoomed in view onto convection. We're still looking at the convection, and in this case, we're here over Mali, southern Mali, and then Senegal. So this is actually mesoscale convective system following the outflow boundary where the new convection is kicking in and actually sustaining this mesoscale system throughout the day all the way to the evening. I will run this one more time. And you can see different shades of colors in this ahead, we could say mesoscale cold front. So this outflow from the mesoscale system, the colors change from purple to blue when the clouds are rising and vertically developing into mature cumulonimbus clouds. Okay, so we've seen Atlantic, we've seen Africa. What about South America? Actually, there is quite a good view over South America. And in this case, you see elongated front across the South America and Atlantic with the different shades of blue and purple to yellow, telling you more about what are the clouds within this cold front. And I will move this in animation so you perhaps spot something else here. In kind of ingested in this cold front, there's something very pink. And if you think about it, it must be smaller particles. If you would know the product, you would know that it would have a lot of reflection for this from the blue component, because the blue components here is the smallest wavelength in terms of the 3 different bands. So that means small aerosol particles, that is smoke. And then Amazonia is pretty active and wider. Actually, then Amazonia is pretty active in fires this year. So it's actually a smoke being ingested in the system. There are 2 more things interesting in this loop. Maybe you missed it. More towards the south of the continent. And there was a kind of greenish shadow moving over the scene. And if I move to true color RGB, maybe you get a better idea about this event. So that was actually the eclipse, moon eclipse, a couple of days back, affecting countries in the southern part of the South America. I will just run it once again. Due to Rayleigh correction and the selection of wavelengths, this is better seen than in cloud phase RGB. Just to compare, maybe you noticed or not, the same image, you had the snow over Andes in blue shades, so big ice particles in the cloud phase. And on top, I pasted the Severi view, natural color RGB. Why? Just to show that actually with FCI, we have a better coverage all across the rim of the full disk view. So can we see North America with FCI? What do you think? So previously, I remember we had a couple of cases, but we didn't look at the North America much with the FCI. And then I received an email from one of the trainers, retired trainers from EUMETSAT, Jochen Kerkman. The title was, there was only a title, and the title was MTG FCI sees New York. And he attached this nice image where you really see the Long Island, not only New York, there's Philadelphia, all the way to Washington. You can see actually quite a lot of the shore there. Okay, moving back to Europe, couple of more examples. This is snow over the Alps, the first serious snow this year. If you remember the cyclone Boris, there was a cold air rushing over the Alps, which you can see in this, I have to say, a little bit affected animation. It can only show the end of it, but we can skip that. Anyhow, zooming into Alpine region, you can see the fine details of orography and the snow amounts. The last major fire event was over Portugal, if you remember, mid-September. And what you're looking at is temperature information from the mid-infrared channels in red to yellow, meaning that hotter fires turn from red to yellow. You also have information on the smoke, but as we are using longer wavelengths, you don't see the smoke pretty well. Hence, in this case, I'm combining the 2. So I'm combining the information about the temperature in green, so you see the hotspots in green, but also shorter wavelengths reveal the extent of the smoke from this event. And I will just run shortly small animation. It was really horrific event there, with a lot of smoke being exhausted into the Atlantic in this case. Okay, talking about aerosols, dust is very well seen. It was well seen also in the natural color of Severi, but even better, especially the thinnest, the finest dust can be seen very well with the geocolor RGB. In this case, we see the advection from North Africa towards Europe of the dust, very actually thin dust layer, not well seen in Severi, however. This is just to give you a context of this event, and I will animate the day before the one conveyor belt bringing this dust up towards the southern Europe. Okay, Alessandro had the example of Etna, but this is really from yesterday. And you can see how faint the signal from the eruption is. If I go to beginning, it's kind of a stronger signal. Why? Because morning and evenings, there is more of because of the geometry of scanning, the more forward and backward scattering from these particles. And you will see, if I move this in time, the smoke will kind of disappear, but it's not disappearing, we just don't see it. Anyhow, going towards evening, we start to see it again. I encourage you to compare this with Severi, with the currently still operational satellite and imagery. You will see how barely you can even, only if you know that the smoke is there, see it. But with the FCI, even the finest smoke plumes can be seen. And just to give you the impression how small the smoke plume is, just by a chance, Jochen Kerkman communicated yesterday he was landing nearby Etna, and he was actually taking some photos, and you can see the plume around about 1340, and I've attached here the corresponding FCI view. So very actually small in terms of some volcanic eruptions, small plume can still be seen with the satellite. Okay, moving towards the north, there are some kind of plumes, but too linear here and separated by angles. So these are thin cirrus, or not so thin in this case. These are contrails, except for contrails, you can see here over Belarus, again, the smoke. And you see some fog patches over very north of Europe. We will see more examples of North Europe, but I'm just attaching here the zoom view of cloud phase RGB, confirming this is low clouds at 1 kilometer. And then if we move to 500 meters of visible channel, we can really see the finest details of the stratus clouds or fog clouds very far away north. So I just remind you, we're moving from the pixel size, say 14 kilometers of the pixel area from Severi to some 5 kilometers or even less, 4 kilometers of the area when you extend the pixels towards the north. So this is really a high ratio between the area size of the pixel and how much more information you can read from it. But it's not only about the pixel size. When you look at this Severi image or one cyclonic system south of Greenland the other day, you can have some impression what is happening here and what are the clouds involved in this view. But if you move to FCI and the 1 kilometer, you, on top of the pure resolution, get the impression of the 3D view by having a shadows and the different angles and the small filaments, for instance, of these transverse cirrus clouds. You get a really much more information about the flavor of the system and what this system is going to do in the next moment. And of course, we cannot skip convection. This is just example over the South Adriatic and Ionian Sea. Few days ago, very strong convection embedded in the this is basically the cold front passing from west to east. Zooming in, I'm giving you a blend of the previous cloud phase RGB and the 0.5, 0.6 visible channel at 500 meters resolution. So you can really observe the smallest details on top of the clouds, cloud shadows all together, but also shadows of overshooting tops, which indicate updraft areas. So really the smallest details can be captured now with the FCI. Just another example, similar area, mesoscale convective system at 1 kilometer of true color, and then we move to 500 meters. You can really see these gravity waves all around and overshooting tops. If I move now to 2 kilometer infrared, in this case, dust RGB, we see considerable degradation of information. However, we have this information 24/7 with infrared, and if you pay attention less to the size of the pixel here, but more of this kind of a more brighter red area, and if you compare this to visible imager, you will notice this is the bulge, basically the core of the system, which can still be seen during nighttime with the dust RGB. And I can tell you with Severi that was not possible at all. So for first time ever, nighttime classification of the cloud top features, not only overshooting tops, bulging of the clouds, but also above and cirrus flow in some cases were observed. Just to give you more impression on this event, I will just leave the loop from the beginning of September of the dust RGB and how 24 hours we can follow some storms and their development and basically analyze their next move. Okay, this is the scene over Eastern Europe, talking about the dust. Do you see any dust? Of course, we had many examples from Africa, but there was a considerable event over Europe, so why not showing that the other day, just the beginning of this month? Do you see dust? Yes, maybe if I tell you, but if we move to dust RGB, we can see that the new dust RGB has really good power of discriminating between the dust and the bare ground. So in pink shades, this is dust just being lifted over the southern Russia here, and just dust that was lifted actually a day ago, already induced in this extratropical system in the bands, cloud bands. Behind the cloud bands, you can see the shades of pink. So just going back and forth, you see actually over the water bodies, you can see aerosols better, but over the land, definitely this dust RGB is performing. And maybe the last thing to show you that we can only use one channel to have useful information. Dust RGB can show you the low level moisture. That was the only way so far. Now we have 0.9 channel, in this case logarithmic combination with a 0.8 channel, to give you the information on the low level moisture. That was my first example over Australia, but now home ground over Europe and over Africa, especially over Atlantic. You can see the adjustment of the tropic air mass through deeper gray shades. The whites are obviously cloud, but around clouds you see deeper gray shades, meaning the moisture is traveling up. Also, you see this band is getting darker due to atmospheric advection of the moisture, and of course the tropical gradients here, obviously over Africa, are very apparent. Tropics are being pretty deep gray due to the low level moisture. Okay, and the very last thing is maybe incentive to you to explore this imagery, because there are features that we still need to explain and give more insights to. For instance, why the clouds are high clouds are becoming brown in close to Terminator in the east, not so much in the west so far that we discovered. Unanswered questions that we still need time to give answers to. You can all help us with that. You're all invited. And with that, I thank you and leave you with a nice storm over South Africa, north of South Africa, Gauteng region. So thank you again. And I take any question if we have
Thank
time,
you.
or we can even move to Petri's presentation if there are no burning questions.
Thank you, Ivan. Maybe you can take maybe just a couple of questions.
Okay.
One first is, how would you suggest to make the HRV cloud RGB with FCI channels?
Mm-hmm. Okay. Yes, this is a good question. I haven't included any example. Actually, that would be, I can go back. This would be the closest to HRV. This is basically combining the best resolution you have. This is 500 meters of visible with any other product. So you do these sandwich products and you take the best of both worlds, better resolution from visible, but also spectral information from other channels. A long answer short, you do these RGBs the same way you did it with the HRV channel by using 0.6 channel.
Okay, thank you. And maybe just a second question, is the FCI Fire product already available? I believe this question is if it's available on EUMETView.
Yeah, no, it's not available. Of course, everyone can construct the RGB on your own. We have this open source SIF tool. We have a SatPy libraries. You can download the data from the data store. From EUMETSAT, it's free, already available to all users, so you can construct yourself. In terms of EUMETView, it's still not there. We are still testing a few other products, but with time there will be introduction of new products, and most likely you will have at least the full set of the RGBs that I mentioned in the very beginning, and these are already a standard set for the third generation imagers, cloud phase, cloud type, true color, including fire temperature RGB.
Okay, thank you very much, Ivan. So we'll answer the questions afterwards. Now it's time to move to the next presenter. Petteri, if you are ready, you can start sharing.
Yeah, hello. It's Petteri Pyykkä from Helsinki. I'm from FMI, Finnish Meteorological Institute. I'm a forecasting meteorologist, and I have some examples how we use the FCI data. And the Nordic latitudes are more like what does it see in comparison to Severi. And I actually noticed when I took this image from yesterday that this is also quite nice. It has the true color in the left, in the middle. There's a cloud phase RGB, and then on the right, the day microphysics RGB, and you can see in the here.
You're still not sharing, Petteri.
Oh, it looks like that it's sharing. Okay, sorry. Can you see it now?
Not yet. It's starting now. Yes.
Okay, now. Oh,
thank
good.
you.
Okay, so in the left, I have the true color RGB, in the middle, the cloud phase RGB, and on the right, the day microphysics. And you can see the different particle sizes in the Gulf of Bothnia in this cloud streets, or I'm not sure if this actually would be called cloud streets since they are like kind of like within the low level clouds. But in the yellow, you can see the water clouds, low water clouds with smaller droplets, and in these pinkish shades, you can see the same water clouds with the little larger particle size distribution, and you can kind of see the same in the day microphysics image. But let's go to the actual examples. So I have two daytime examples and two nighttime examples, and first I will have the similar example as Ivan already had. So there's some fog stratus in the mid parts of Finland. So on the left I have the Severi day microphysics RGB, and on the right the same product from FCI. And as you can see, there is quite a big change, the improvement in resolution when we use the FCI imagery. And for example, here in Western Finland, there are some areas with very well, how would you say that, the narrow or small areas that the fog is covering that are not visible in the Siberi instrument at all. And also the lines or the edges of the stratus fog clouds, they are better visible in the FCI imagery. And another thing that I noticed here at the end of the Gulf of Bothnia, to the north of the city of Oulu, if we had somebody to call from this area when the cloud is dissipating, given only the severe image, I would give this cloud, I don't know, knowing that it's 7 UTC and 16th of September, we still have some sunlight left. I would probably give it like 10 to 15 minutes, maximum 20 before it dissipates. And looking at this FCI image, it looks like it's actually not very thin, but it could stay there even 30 minutes or more. So in this kind of situations, it could help. And I just thought of another example. Imagine that we have fog advecting from the south over Gulf of Finland here to the south of Helsinki, and we have Helsinki Airport about 15 kilometers to the north from the coast. So I don't know yet, but it might be possible that in this kind of situations, if you have fog in the lowest layer and you have some mid clouds or even some cirrus above that, it might be possible to see the fog layer advecting northwards if the mid-level layer is breaking up, and of course that the cirrus layer is not the thick either. We have some examples using the polar satellite data, but it is to be verified whether that's the case in FCI, that you could actually see the fog advecting northwards or southwards. But in this case, when you think about the airport, so the northward advection would be the most important usually. And then there is another example, this from the north of Finland, so around 67th north, the latitude circle. So I have some embedded CBs within a frontal boundary. They are actually visible also in the severe data on the right, in HRV clouds RGB that I put on there. But you can imagine a nighttime situation that you couldn't use the HRV there, and then you would lose this information, but you would still have the IR channels even during the nighttime. So, but if you look at the daytime example that we have here, so the contrast between the how would you call it, the layer, frontal cloudiness layer, and the CBs that are pushing through it, it's quite good. Whereas in HRV channel, it's not too bad, but you cannot really see some of the smallest CBs here. And then I have two nighttime examples. This is actually my favorite, since I'm in a group that forecasts road weather for Destia. The Destia has the road weather center here at FMI 8 months a year. So to them, it's crucial to know when there is a risk of breaking of the low cloud cover after some rain, if there's a risk for freezing surfaces. So once again, I have an example from northern parts of Fennoscandinavia. That it's from around latitude 67, 68. Again, this is from northern Sweden, and you can see within this circle, for its first in the night microphysics, it's quite hard to tell that the cloud is breaking up. You might be able to see that somehow if you animate this satellite loop, but it's looking at only this one image is quite hard. But on the right, you can see some breaking up of the cloud cover. And I remember being in shifts quite many times during the night, thinking whether the cloud might break up even in southern Finland, so the latitudes of around 62, 62, 63 north, and it is quite tough sometimes to see the small patches in the night microphysics RGB. So this is quite a big improvement, I would say, when it comes to monitoring the risk of breaking up of this low cloud cover. And the last example, I have the trapped Lee waves in central Sweden, Norway. So with the westerly, might be northwesterly flow in this case, and the mountain wave turbulence was not actually forecast in this case. I checked the significant weather charts for the aviation, but you can still see looking at the FCI on the right, you can see the wave structure here. There's an animation coming soon, so you can see it better. But looking at the same image from Severe night microphysics RGB, it's quite hard to see if you have looked at this product many times, you can actually see it somehow, but it is very easy to miss, I would argue. So if we take a look at the animation, I didn't circle the area, but here on the right in FCI, it is quite nicely and clearly visible these mountain waves in this region. Whereas looking at the Severe only on the left, it is quite hard to spot the formation of these trapped Lee waves. And what else you can see in this image actually? This is actually one of the images that we posted on on our social media. So there is this a low-level cloud. There was some fog in it too. That was advecting from the north, also to Helsinki airport. So here we have an example of the advection from the north. With the FCI, you could clearly also see when exactly the advection is happening, but it is not a big improvement to FCI. It's more like the other phenomena that I showed you here. But yeah, thank you. Is there some questions? I think now is the time to ask questions from the previous presentations too. There was still some.
Thank you very much, Petteri. Very exciting to see how far north can this FCI instrument be used. This is really good news. So let me try to share the Slido so that we can still answer some questions. So I think these are still for Ivan. So first is on the image that you showed over South America with the smoke. Which composite image was that? I believe it was the true color, but you can probably...
Yes, that is the true color, and the true colors consist of 1.6, 2.2, and 0.6 channel, red, green to blue. Hence, the smaller the particle, you can see it with the smaller wavelength. So mostly is blue. If you have a little bit of red, then it turns to purple, magenta, because 1.6 could see a little bit of that smoke, meaning that the particles were actually a little bit bigger. So probably intense fires from Amazonia in purple.
And I think you are already partially answering the following question. So true color RGB uses shorter wavelength channels than the natural color. Would this mean it is more suitable for smaller particle detection, but less for bigger?
Yeah, well, yes, that's true. It's better for smaller particle detection, and then there is no difference for the bigger. It doesn't reduce the power for the bigger. If you think about, if you can see a small ant with a magnifier, you can see also an elephant with the same one. But anyhow, you get the gradient. You kind of can understand the difference between the smallest particles to mid-size to larger particles, going from really 0.4 to, in the solar region, 2.2 or 3.8 microns. So I think the power of discriminating the size of the aerosol particles will be much better than for Seviri.
And so would it be easier to distinguish dust from fog? And this is the next question.
Yeah, so definitely the answer is yes. Both are aerosols. Basically, clouds are aerosols, but definitely clouds have a different spectral signature than the dust. And of course, it will be much easier to discriminate the dust from smoke, for instance, because the dust particles are much bigger than smoke particles.
Okay, thank you.
Yeah.
And another question, should we use both geocolor and true color RGBs?
Yeah, this is geocolor RGB. The intention is to have eventually maybe even the lightning data, maybe fire hotspot information. The idea behind geocolor is let's have in most natural view everything that could be taken from the level 1 FCI, or in this case, if we include lightning, as Alessandro showed, LI data. So through satellite readings in level 1 in terms of RGB, there is no model data. It's a pure satellite data, more or less in one view. Of course, daytime, the best closest to what you get to what your eyes can see is the true color RGB. And during nighttime, the most important thing is to discriminate between the low clouds and the high clouds, especially see these smaller filaments of lower level clouds. In the best resolution, it can be 1 kilometer because 10.8 and 3.9, and their difference to discriminate between the low clouds and fog is at 1 kilometer. So it will be pretty powerful. Of course, the true color is kind of redundant to geocolor, but if you there is small differences, especially in the transition zone, in dusk dawn moments where you best see your smoke plumes or dust particles. Maybe you would be more keen to use true color RGB, but altogether, if you have geocolor and you don't mind having maybe lightning on top and city lights during nighttime, then it's better to use geocolor. It's anyhow 24/7 product.
Okay, thank you. Now, question for Petteri. In the last nighttime microphysics RGB, there was a purple dotted stripe. So you're sharing again your screen?
Yeah, it's probably
yeah.
this. I was thinking about this too. I couldn't think of anything else, that ship track or artifact, but I would guess it's artifacts. Do the ships leave this kind of plumes where it's not coming constantly from the ship? So what would the EUMETSAT people say?
Well, I don't remember the image per se, but yes, usually if you have ships or even other sources of aerosols like industry, maybe a chimney, then if this chimney or a boat ingests particles, basically kernels for condensation into the existing cloud, it will change the microphysics, change the size of the particles to smaller, which then can be in a spectral sense read from the RGB. Yes.
Yeah, I think it's an artifact, this one, because you see it's also going on land. I think this is what is that? That's RGB, this one.
No, this night
Oh.
microphysics.
Night microphysics. Can you remind me the bands that you use? Sorry.
Can you open the image, maybe?
Yeah, the image is there. I shared it. Or
okay.
Oh,
I mean, does it? Because now I don't remember all the RGB's recipe. Does it contain the 12 micron?
Yes, it does. On the red, it's 12
the
minus 10.
So there is a dead pixel on the 12 micron, and when you do the resampling, this is level 1C. So when you do the resampling, you see this type of patterns because there is one dead pixel. We are uploading now the new pixel maps, and this is why you have this type of stripes and artifacts. So it's actually a dead pixel, and this is what you have.
Thank you.
Okay, thank you.
Thank you.
And the last question with the FCI night microphysics, is it possible to distinguish convective clouds from stratiform clouds?
Using the night microphysics. Yes, I would definitely say so. I was trying to look for a summertime example, but we are currently only saving the 2 weeks of data because of the data volumes are very big. But I would definitely say so. And you can also we have done some proxy images of the FCI data before it was it came alive. So we could see that it is even possible to see some overshooting tops in the high latitudes using the FCI data.
Yes, if I may add, there are two things related to convection that are better with FCI. One is that you can upscale your resolution because you're using 10.5 and 3.8 channels, which are at 1 kilometer. So you can kind of enhance the resolution and see the structure of the clouds better. Usually, convective clouds are more round than the stratiform. Only from the shape you can take that information. But the other thing important is especially for night microphysics, the big problem with Severi was that the 3.9 channel in that case was saturating at low temperatures. So you had kind of artifacts all across your cold anvil tops, which is not expected to that degree with the FCI, and I haven't seen these. Usually these are green dotted pixels that you can see on top of the cold clouds, which are not foreseen with the FCI. So definitely improvement in the dynamic range of the infrared channel.
Okay, thank you for clarifying. So I think we are ending this session. Gerrit has a hand raised, but I'm not sure if we can give him a possibility to unmute. Can we? Or yes, maybe you can add. You want to add something, Gerrit?
Oh, he's saying that it was a mistake.
Okay, no problem. Good. So I want to thank all the presenters for today's short course. So this session was recorded and it will be available at the EUMETSAT short course Moodle page. We will continue to offer a series of short courses on MTG data and applications. So stay updated by checking our user portal or the training events calendar at trainingevents.eumetsat.int. Thank you all the participants in this short course, and I hope to see you all next time. Thank you.
Thank you all for coming, and see you for the next one.
Thank you. Have a good rest of the day.
Bye.